Hello, my name is Nicholas Reed, and this is my lab for oscillation for Physics 2211 at Georgia Tech, semester of fall 2020. So some key equations we'll be looking at during this lab are Newton's second law, kinetic energy, gravitational potential energy, and spring potential energy, as well as the change in those energies as it goes through time. So we have them all here, just for basics. So our experiment this week was mass extent suspended by a spring. The mass had a mass of 0.402 kilograms. Spring stiffness is at 6.84 newtons per meter, and the resting length is 1.3123 meters. The mass is pulled and introduced to motion, track motion using code, and we tracked the motion using code and also predicted it using code. This way we can compare the actual to the predicted and plot the actual movement of it. So this is the video that we used to analyze. Regular swinging around. Alright, so then we plugged it into tracker in order to get our actual data points. This is the video. You can see we tracked it throughout its motion as it goes around. I tracked 100 points just to give me the most accurate data possible. And you can see as it moves around oscillating motions. This is plotted on the X and Y. This is just showing the Y for right now. So then we take the experiment results and we start creating a code to go along with it. So this part of the code is just setting up our visual parts of it. So we set up the ball of the predicted one, which is going to be blue. We set up our spring, which is going to be cyan, and then we plot our curve, what our data points are going to be on this graph. So we have kinetic energy being blue, we have gravitational potential energy being red, we have spring potential energy being green, and we have total energy being orange, as well as setting up the actual data points ball, which will be represented by a red ball. Then we set up our initial conditions, which is we set up the mass of the ball, we set up the initial position, which we found from the tracker, and then we also set up our time as well as our time step, which was given to us to match the time step of the video. Then we move on to our interaction constants and spring energies. We set up the gravitational energy, we plug in our spring constant, which we had calculated, and we plug in our initial length, which we also calculated, or rest length. So then we find L hat by finding the distance from the origin by the ball's position. We find L hat by finding the dividing the vector of L by the magnitude of L in order to get L hat. And then we find the actual distance by subtracting the magnitude of L by the relaxed distance. So then we can find then we have to find the energies of the system to start with, and then we have K equals 1/2 times the ball's mass, or the kinetic energy equation. We just use that to plug this in. The mass times the velocity squared. Then we use the gravitational potential energy equation, the mass times the gravity acceleration times the distance vertically. Spring potential energy equation, find 1/2 times the stiffness times the distance stretched raised to the second. And then we find the total energy, which is all these energies summed up. Then we have our calculation loop here, which we first start with. We define all our initial values going into each loop. And then we find the force due to gravity, which is just the acceleration times the mass. Then we find our spring constant, which is the spring stiffness times the distance stretched times L hat, which will give us our direction. We add these together in order to get our net force, and then we use our velocity update formula derived from Newton's second law in order to get us updated velocity, as well as the position update formula in order to update the ball's position as it moves around attached to the spring. So we update L and then L hat and then as well S. Same equations from earlier, just we're updating them each loop. And then I used negative L to plot my spring in order to track the ball properly. Finally, we come down, we re-update K, we re-update kinetic energy, we re-update gravitational potential, and then we update the spring potential energy. And then we also update the total energy. And then we find the difference in each one by subtracting the updated one by the initial one from this each loop. And then we can plot this. So we plot that with the colors right here, and then we update time step down here. And then this is the rate it's produced. So this is what we get. The red one is the actual, and the blue is the predicted. And then we have our graph up here showing that the energies cancel out, and the orange energy, which is total energy, is almost completely flat, which shows that the energy is conserved in this, since there's no dissipated forces. There's no dissipated forces calculated in this equation. And then you can see that the position that is very similar, but the actual tends to dip off a bit. This is due to dissipative energies, which take away from the ball's energy due to heat and drag, as well as a few other possible things that could have taken away the energy of the ball. So then we move into the analysis of the energy principle. Since the energy principle is satisfied, there is no transfer of energy into and out of the system. This is shown by the flat graph of delta E. So we know that all the energies cancel out, which means that the system is not receiving or giving energy to the surroundings, which is a closed loop, which implies that delta E equals 0, and it meets that. But if we were to just look at the actual versus the predicted, we would be able to see some dissipative forces. And then the period, we can estimate the period from the x as well as the y position by finding each time the peak is reached. So here and here for the x estimate, and then I think I used this and this peak for the y estimate since they are the first ones and they have the least drop off in energy between the two. And I use this to find the period for each one. As you can see, they're pretty similar. Y is a little faster. I believe this is due to the since it was pulled farther in that direction. All right, that is all. Thank you for listening, and have a great day.